Alright, we're looking today at Venn diagrams, which are diagrams that we use to represent sets of objects, numbers, or things. We use the capital letter U to refer to something called the universal set, which includes all of the numbers or objects that we're going to be examining within the context of that particular problem. And we'll represent this graphically as a rectangle, and then any sets within our universal set are represented as circles or ellipses, which is like an elongated circle, like an oval. So a few of the concepts that we were looking at in the sets unit, sets lesson before, included the complement. So here's a diagram of the complement of set A. You'll see that the shaded region is everything outside the circle A, meaning that these are all of the elements in the universal set that are not in set A, which is why it's often referred to as A not. Let's look at the concept of a subset. If B is a subset of A, then we know that B is entirely contained within A because every element of B is inside A. And so this is a diagram of a situation where the set B is completely contained by a larger set A, so we would say that B then is a subset of A. The intersection between two sets, like A and B, is denoted by this sort of upside-down U-like thing. And I think it looks a little bit like an N, and so I remember that the N is the intersection, and it refers to elements that are in both A and B. And so you'll see that on the diagram, that's going to be everything that is inside A and B at the same time. That is to say, this overlapping shaded region is the A intersection B diagram. The union, on the other hand, includes everything from set A or set B, or both. And so I think of this one, the union, as the MasterCard symbol. You know, the credit card MasterCard, which has got an orange circle and an overlapping yellow circle. Everything that's orange or yellow is a member of the union of A and B. And another way you can remember this is that this U symbol looks kind of like a big container, as if it's able to catch rainwater or anything else that's falling in. And so you can think of the union as it just catches everything from sets A and B, and we would write all of the elements from A or B down into one big set. And disjoint sets, otherwise known as mutually exclusive sets, on a Venn diagram we would draw them like this, as two completely independent circles with no overlapping region at all, because they don't have any elements in common between them. So we want to represent this and ensure that we're demonstrating that there is no intersection by having them completely non-overlapping, so that this intersection region doesn't even exist in this diagram. That makes it very clear that they are disjoint sets. Alright, so a few examples. Suppose we've got the universal set 1, 2, 3, 4, 5, 6, 7, 8. Let's illustrate on a Venn diagram the sets A, 1, 3, 6, 8, and B, 2, 3, 4, 5, 8. So, I'm going to begin by drawing the rectangle box, which is my universal set, so I'll label it with a U. It's very important that we label the box and all circles inside with their corresponding capital letters. Let's draw now my set A, which we know contains 1, 3, 6, and 8. And I'll label it as set A. And we also have set B, which contains 2, 3, 4, 5, and 8. Well, 3 and 8, it turns out, also belong to set A. So that must mean that 3 and 8, because they're in both A and B, they belong to the intersection of the two sets. So 3 and 8 are inside B. We've also got 2, 4, and 5 inside set B. but not members of set A. And I haven't included every single number yet from my universal set. 1, 2, 3, 4, 5, 6, 7, 8. I haven't included the 7 yet. 7 does not belong to set A, nor does it belong to set B, but it is inside the universal set, so I'll write it on the outside. It's inside U, but not inside circles A or B. Alright, example B. Again, we need to draw a Venn diagram that starts out with a rectangle on the outside called the universal set, which is again composed of the numbers 1 through 8. Inside set A, we've got several numbers, 1, 3, 6, 7, 8. 1, 3, 6, 7, and 8. Whoops, let me just draw that in a slightly different place. You'll see why in a minute. 8. Okay, and that's set A. Now have a look at set B, which is composed of the elements 3, 6, and 8. Do you notice anything? Yeah, you might have noticed just now that 3, 6, and 8 are all members of set A. That means that set B is entirely contained within set A, and thus set B is a subset of set A. So I'm just going to neaten this just a little bit so that it will be easier for me to draw my subset. So my 3, my 6, and my 8 are all occurring in the subset called B, which is entirely contained within set A. And let's just make sure that looks like a B, not an 8, okay? And I haven't done everything, have I? Because I've still got the numbers 2, 4, and 5 from the universe that haven't yet been represented in my Venn diagram. Now all 8 of my universal set elements appear. Next example. So I've given you this Venn diagram with the letters A, B, C, D, E, F, G, H, I, J, K, L located in various places inside the 3 sets A, B, and C. And we need to list all of the letters in all of these 8 different examples. So let's just set up the answers first, and we know that I need to create a set of letters, so I'll open up my curly braces in each example. Alright, here we go. What are the different elements inside set A? Well, let's think. I've got, remember, I'm not looking for only the ones that belong to only set A. I want everything inside set A, which is everything inside this circle, including these letters that exist in other sets as well. As if they're a member of set A, we have to write them down. And so we've got then A, B, C, D, H, J. A, B, C, D, H, J. And you don't need to write the letters down in alphabetical order. Of course, it's nice if you do, because then you can compare your answer to somebody else's who's done it in alphabetical order a lot quicker. Set B contains then A, it doesn't contain B, so A, C, D, E, F, G, and K. A, C, D, E, F, G, and K. And one thing we can always do, just to double check that we haven't left anything out, is that we can count the number of elements inside set B. 1, 2, 3, 4, 5, 6, 7, and count the number of elements that we just finished listing. 1, 2, 3, 4, 5, 6, 7. Okay, looks good. Set C, we've got A, B, E, F, I, and L inside set C. So A, B, E, F, I, and L. Oops, that's the wrong parentheses at the end. Let's make sure it's one of those curly braces. Okay. Part D, A intersection B. The intersection means that we're looking for elements that belong to both A and B at the same time. And you might recall from our Venn diagram earlier on that that looks like the overlapping region. So let's find out where A and B are overlapping. And we can see that A overlaps B in this region right here, containing the elements A, C, and D. Meanwhile, A union B is catching all of the elements that belong to A or B. So we've got all of the elements in A, B, C, D, H, J, as well as the elements that are in set B, E, F, G, K. I've already counted the A, C, and the D. I don't need to count them twice. Alright, so let's list them all then. A, B, C, D, E, F, G, H, J, and K. In fact, it's everything in the universal set except for I and L. I and L don't belong to A or B. Part F. B intersection C, so the overlapping region between circle B and circle C contains A, E, and F. A intersection B intersection C. This means that we're looking for the place where A, B, and C, where all three circles are overlapping. Another way of arguing this is that we're looking for the elements that belong to all three of the circles at the same time. Well, the only place that the three circles are overlapping everywhere is right here in the middle, and so it only contains the element A. And lastly, A union B union C. That catches everything in A plus everything in B plus everything in C. Well, look, that's clearly everything inside my entire universal set. And so I've got then all the letters from A through K. A, B, C, D, E, F, G, H, I, J, K. Oh, and also L, right? Yes, okay. Great. Last example says, given a Venn diagram, and then, whoops, there isn't a Venn diagram here. Let's draw a Venn diagram. So here's our universal set. And in it, we've got two sets, A and B. I'm going to make a little bit of an assumption for a moment that A and B do overlap like this. Of course, it's possible that they're disjoint, or it's possible one is a subset of the other, but let's just assume that they look like this for the time being. We've been told that there are 26 elements inside the rectangle, the universal set U. I don't know what those 26 elements are, but I know that there's 26 things in the rectangle somewhere. 11 of those things are inside circle A, 12 of those things are inside circle B, and there's 8 things that are inside the intersection between A and B. This is the key to the problem right here. We must start by putting in that there are 8 elements inside the intersection. That doesn't mean that the element called 8 is the only thing existing. I realize that according to the previous notation, you might think that. I'm now using this notation in a different context, where these numbers now represent the number of elements that exist in that place. So we can see that there's 8 things belonging to A and B at the same time. And remember that there's only a total of 11 objects inside set A. So if we've already got 8 of them inside circle A, and there's a total of 11 inside circle A, how many must be left over to go in this region here? Clearly, 3 of them. 11 minus 8. And if we've got 12 objects inside circle B, and 8 of them have already been used in the intersection, 12 minus 8 leaves only 4 to go on the outside. This allows us to already answer part A, the number of elements that are inside A or B. So A or B is going to be 3 plus 8 plus 4. And we've got a total of 15 elements inside A or B. Now actually, I didn't write how many elements are outside A or B. If I've got a total of 26 elements and I've already used these 15 of them, 26 minus 15 leaves 11 on the outside. And the last problem, how many objects are inside set B and are not in set A? Well, these are the ones inside set B. These are the only ones that are not in set A, and so the answer is 4.